All right, so let's move on and talk about calibration and validation. So external calibration curves, you're going to create 4 external calibration curves for the experiment, right? Because you've got 4 different analytes, and each one of those is going to have a different response factor. So you guys are very familiar with this at this point. Creating external calibration curves should be second nature. So I'm not going to go into that in detail, but in your reports, what we want to see is a figure like this, where we're seeing all 4 of our of your analytes, and you might want to start working on combining these into one figure with multiple panels like this, labeled A, B, C, and D, just so we don't have to scroll through 4 separate pages to find all 4 of your cal curves for the external cal curve. All right. But what is new this time is our standard addition calibration. And we're going to use a method called the constant volume x-intercept method. There are a bunch of different ways to do standard additions, but this is the one that we're going to focus on. All right, so the way standard additions work is that you are going to prepare a cal curve, but your cal curve is also going to contain an amount of your unknown solution. So to each of these calibration solutions here, we're going to add the same amount or the same volume of our unknown solution. So how much should we add? Well, these are going to, we're going to add 5 milliliters of our unknown solution. How are we going to do that? What materials should we use? Because we are working in organic solvents here, and we're interested in, or we're quantifying plasticizers, we want to stay away from all of those plastic materials we used with the wine experiments. And we're going to use glass volumetric pipettes. And the total volume here is going to be 10 milliliters. So we want to use 10 milliliter vol flasks. First thing we're going to do is add 5 milliliters of our unknown solution across the board. Next thing we're going to do is we're going to add varying amounts of our phthalate stock to each solution. So this is how we're making the calibration curve, essentially. What range do we want for our calibration? 10 to 100 parts per million. All right, this is the same range that you want to use for your external calibration curves. All right, so if you're making up your external calibration solutions in 10 milliliter vol flasks, you should be able to use the same volumes of your stock to add to your standard addition solutions as well. And how are we going to add our stock? We have those Hamilton syringes available. So an example here of the amount of stock that we want to add on top of our 5 milliliters of unknown sample. We always want to have a 0. That's very important to have in this calculation. And then, we're going to add increasing amounts of our stock to get a calibration curve. How many calibration solutions do we need to make? We're going to want to have 7 calibration solutions so that we can, if something goes wrong with a couple of those, we can still have at least 5 calibrations. All right, once we've created these solutions and we run them, we're going to get something that looks like this. So our response, which is labeled A here for absorbance, because I took this from a different example, is on the y-axis. And our concentration of the standard, just the concentration of the known amount that we added, is on the x-axis. And we're going to plot our calibration solutions, and all of yours are going to look beautifully linear like this, but of course yours are going to have error bars showing the standard deviation. And then we're going to fit a line of best fit through there. What we want to do is then extend this line of best fit back to its x-intercept. All right, because we've got that unknown solution in all of these calibration solutions, our calibration line is not going to pass anywhere near 0, 0 because we're always going to have some concentration of analyte in the solution from the unknown. So what we're going to do is trace this line of best fit back to the x-intercept right there. And then the absolute value of our x-intercept is going to be the concentration of the analyte in that solution. Okay, so very simple graphical way to determine this concentration. All right, but thinking about this, there's something else that we're going to have to do to get back to our final concentration in the unknown sample. And hopefully it's apparent to you based on what we talked about up here, where we're adding 5 mils of our unknown, and then we're bringing it up to a total volume of 10 milliliters. We also have to account for that dilution. All right, so let's do a quick example here. So I've made up some dummy data here. Here's our standard addition calibration curve. Again, concentration on the x-axis and peak area on the y-axis. All right, and in this example, I used a total volume of 25 milliliters for each solution, and I added 10 milliliters of my sample to each solution. So what is our final concentration going to be? The first step here is we're going to look at our equation for the line of best fit, and dropping the uncertainties out of here. For now, we're going to have y equals 52x plus 790. And we're going to rearrange this to solve for x. All right, so x is equal to y minus 790 divided by 52. And then because we want to figure out where our y or our x-intercept is, we're going to set y equals to 0. And then our equation becomes minus 790 divided by 52, which at 2 sig figs is minus 15. All right, so we're going to take the absolute value of that, and we get 15 parts per million as our concentration in that in the solutions that have been diluted. All right, so now we need to account for the dilution factor there. So our 15 parts per million is going to have to scale that back up by multiplying by the total volume divided by the sample volume that was added to those standard addition samples. So when we do this, we go from 15 ppm up to 38 ppm for our final concentration in the unknown. All right, so you're going to do similar calculations for all of your for your 4 analytes in your standard addition samples. All right, so whenever we report a concentration, we also want to report the uncertainty. And to get to the uncertainty calculation for standard additions, it's slightly different than what you're going to do for your external calibration curve. So what you're going to want to do is go back to SCOOG, go back to your instrumental textbook, and look at page 15, figure 1-11. And it's going to walk you through the Excel calculation for determining the uncertainty in those concentrations. Now, if you do this and you get concentrations that are very different between your external calibration curve calculations and your standard addition calculations, is that normal? Do you think they should be very different? The answer is no. Right? They shouldn't be different if you've accounted for that dilution. They should be pretty similar. If they're not similar, that means that something has, there's some difference between the way that you prepared the standard addition and the way that you prepared your external calibration curves. Now, with more complex samples, we're giving you 4 phthalates dissolved in dichloromethane. If these were a more complex matrix, like blood or urine or something else like biological tissue, you might see differences between external calibration and standard addition because there might be some matrix effects that the external calibration curve doesn't account for, where the standard addition curve will account for that. That's one of the big advantages of doing standard addition, is that it's automatically accounting for any differences due to matrix interferences, because you have that sample matrix in every one of your calibration solutions. Right, so standard addition, if you've got a really tricky matrix, is oftentimes the gold standard for producing the most accurate, reliable results. All right, so let's talk quality control. Like I said, we're not using surrogates or internal standards here. You could do that easily with this experiment, but we're not asking you to do it. We are requiring you to run a full suite of quality control samples for both the external cal curve and the standard addition. So what's that going to look like? For our external cal curves, you guys know these. This is LRB, LFB, LFM, and MDL. For the standard addition curve, we got to think a little bit harder about this. So can we run an LRB for our standard addition curve? Kind of. Our LRB is just going to be our diluted sample. So it's going to be that 0 calibration curve point, essentially. Can we run an LFB? Kind of. We could run an LFB, but our LFB is going to have matrix in it because we've added the sample to all of our, we have to add the sample to all of our solutions. So our LFB is going to be essentially an LFM. And then can we run an MDL sample? Yes, we can run an MDL sample because that's going to be our diluted sample plus a small amount of our analyte. All right, last thing to discuss here is safety. So we're using dichloromethane. And again, this is, it's a pretty nasty compound, so we want to use it in the hood. You don't want to spill it on yourself. Always wear gloves, goggles. If you do spill it on your gloves, take your gloves off right away and swap them out for clean gloves, because it can go through nitrile gloves if given enough time. All of these phthalates are also, like I mentioned in the beginning, toxic compounds suspected of causing some nasty endocrine disruption in animal systems. You are an animal, so let's try and be clean when we're using the balance. Make sure that we're not getting these all over the place. One thing that I neglected to mention is that some of these compounds are going to be crystalline, they're going to be solids. Others are going to be liquid at room temperature. So when you're adding these to your standards, if it is a liquid, you're going to have to use appropriate delivery mechanism and not be spilling that all over at the balance. All right, and we are going to have a special waste container for this.